been 5 long days since I've seen you. Very upsetting. So I started recording. I just wanted to mention a couple of things. First off, I did finally go back and put the class recordings on the class meeting pages. So I've been meaning to do that like right after class, like after the same day, and I just kind of got behind on it. But I went back at the end of last week, and so you can find the recording for every class on the class meeting page. And you'll notice that I put the old weeks down below. So the current week. Yeah. Okay. So that's all good. Also, I haven't mentioned this, but do you get notifications when your problem sets are finished grading, or do you see on Gradescope that maybe you don't get an email, but okay, but like when the graders are finished, they publish the grades. So if you're going to Gradescope frequently anyway, so probably you notice that you do have graded homework there now. So the graders are keeping up pretty well so far, it seems like, which is good, and I'll keep on them to make sure that that's happening. But if you have any questions about homework, grading or anything, I mean, the graders themselves are kind of harried and don't get paid for that many hours of grading, so they may not give like full feedback. So anything you want to talk about, just come to office hours or send me an email, and I can like look at that problem on your Gradescope, or I think you can even submit like a regrade request on Gradescope, which I'm happy to take a look at and put a more detailed comment on if there's something that you feel like I don't understand why I lost points, or I don't understand what I'm missing here. But the best thing is always to come talk to me if you can, one-on-one, because that's where the most insight happens. So, and yeah, please come. You guys haven't been coming to office hours that much. Maybe the problem sets aren't hard enough yet. Maybe I should make them harder. But yeah, I think of my 3 classes, you're the ones that are going to office hours the least. So come see me. I'm just down the hall. I'm there all the time. I have all those hours that I list on. And then Finn, I hope people have been going to see Finn. It's kind of nice. He just has the Zoom. Oh, I keep meaning to update this. I'm sorry, but he emails at least every time about his availability, right? So, okay. So we were talking about, we sort of did the parametric vector form of solutions of a system of linear equations. The thing I want to do today is actually, wait, let me change to, I want to go back to this handout that we have about linear combinations of vectors, because we haven't talked about linear independence. And I'm sort of trying to go along with the book. So like the book did span, like maybe in 1.4, and then 1.7 is linear independence. And then they don't really talk about bases, a basis or bases, I think, until later in the book, but I want to go ahead and put this idea in your head. Because we've been dancing around a while with like taking a matrix and row reducing it and looking at the pivots and trying to interpret things. And I kind of want to put it together and think like, what kind of qualitative things can we say? And then, so I want to define like linear independence carefully, basis carefully, talk about some of that stuff. Yeah, and then, right, because the next big thing will be linear transformations, which is a completely different way to interpret a matrix. But I want to sort of get all our ducks in a row before we move on to that. Sort of understand everything as well as we can. So I want to talk about what linearly independent means, because I sort of said there's these 2 things, span and linear independence. And so let's look back at this example of these 3 vectors, and I'll just write them on the board. So I just want to, because we did this example, right? And so let's go ahead and look at it. So let's call this under the general heading of linear independence. Linear, I guess, independence or dependence. Sometimes it's independent, sometimes it's dependent. So consider these 3 vectors. So 4, 1, -1. These memorized by now. 2, 3, 1, and 1, 4, 2. Is that what they are? So what did we find out? When we looked at these, we saw that they only spanned a plane, right? That they ended up being coplanar. So they didn't span all of 3D space, right? This is from earlier. We looked at these earlier. So we found that the span, remember the set of all linear combinations of a collection of vectors is the span is a 2D plane. Not all of 3D space. And the way that we saw that in the matrices is we took the matrix whose columns were V1, V2, V3. Let me just write that down. 4, 1, negative 1, 2, 3, 1, 1, 4, 2. And we row reduced it. And so one point I wanted to make today is that like I think we've row reduced enough that we should really just ask computers to row reduce for us. So let me do that real fast. So if we do this 3 by 3 matrix, oops, wait, what happened here? Sorry, I'm just going to do this real fast. Just trying to make the point that we're getting sick of actually row reducing by hand. And that's not too hard, right? Reduced, yes, okay. So, where did it go? Now they actually show you the whole process and give you this. Okay, so right. So it row reduces to that with the -1/2 and the 3/2. Yeah, I thought that was what it was, but I didn't remember. 1, 0, 0, 0, 1, 0. -1/2, 3/2, and 0. Right, so it row reduces to that. And okay, but then how do we interpret this? So there's a couple different ways to interpret this. One, right, is like, I want to kind of look at this, the row reduced form, because we could think of this as an augmented column. We can think of the third column as augmented because there's only 2 pivots, right? If this had row reduced to sort of the most standard thing, like the nicest thing, where there were 3 pivots, that would actually say that these vectors span all of 3D, right? Because we could augment this with anything and we would get a solution. So we can generate every vector from these 3 vectors. So if this was true, then the span of V1, V2, V3 would have been, yeah, that would have, let me just write that down, would have been all of R3. Okay. But it's not, it's this, and this is what's, the fact that there's only 2 pivots suggests why they form a plane, right? But the 2 pivots instead, in actuality, indicate that the span is 2-dimensional. I sort of said that, right? But we haven't really sort of justified it completely, and I want to sort of talk a little about how to do that. But in particular, if we think of this as an augmented column, the third one is an augmented column, we can actually get the third vector as a linear combination of the first 2, right? Because if we reinterpret this, yeah, in fact, if I augment, let me augment this column too. So like, we can think of this guy right here as x1 times 4, 1, negative 1 plus x2 times 2, 3, 1 equals 1, 4, 2, right? That's a way to interpret what that is. If we're thinking of this last column as augmented, right? This is like the column, right? We could write that as linear equations by putting the x1s, by combining everything. But, and so then this right here says that x1 is -1/2 and x2 is 3/2, right? So In other words, we can check this, -1/2 times 4, 1, -1 plus 3/2 times 2, 3, 1. Well, let's check it. So -2 plus 3 is 1. -1/2 plus 9/2 is 8/2. 4. +1/2 plus 3/2 is 4/2, 2. Okay. So that's how we read off, like if we want to think about how something's a linear combination of the others. And what that really means is that the third vector is unnecessary in the span, like it's sort of a redundancy. It's like an extra thing that once we have those first two vectors, the third vector doesn't actually contribute anything more to the span. So, right, -1/2 v1 plus 3/2 v2 equals v3. In other words, and one way to say this would be that the span of the first three vectors, the three vectors, is actually equal to the span of the first two vectors. Right? But the third vector, v3, is sort of redundant. Yeah.
Is this all for all cases?
This is for these three specific vectors. Yeah. Right. If they had reduced to this, then you would need all three to create all three dimensions, sort of. Good. I'll say also that because we sort of chose the row reduction algorithm, I mean, there's a thing here that's kind of funny that we make the staircase pattern like this, but somebody could have decided they want to make the staircase pattern like that instead, or like from the bottom or something, you know, it's a convention. So the third vector is a linear combination of the first two, but I could also write the first vector as a linear combination of v2 and v3, or the second vector is a linear combination of v1 and v3. So when I'm saying v3 is redundant, I mean, any one of them could be redundant. And the other two. So I want to just make a point of that because that's an important idea that we made some convention about how we do this row reduction algorithm. So really, any of v1, v2, and v3 is redundant. We can write any as a linear combination of the other two. So we could say, I actually want to do this because I want to illustrate this point. Like, if I multiply through by -1/2 and subtract, we could say v1 is going to be, I think, I do this in my head, 3v2 minus 2v3. I just did some very dubious algebra there. Like, I tried to multiply through by -2. And then add the v2 to the other side. Did I do that right? Anybody checking me? X coordinate works. I'm just like looking at those three vectors and trying to calculate the right-hand side of that. The X coordinates, oh no, wait, it doesn't work. Oh no, it does. 3 times 2 is 6 minus 2 times 1 is, yeah, so 4. Okay, so I think that, or v2, we could write, if I multiply the whole thing through by 2/3. So I think that's 1/3 v1 plus 2/3 v2, et cetera, right? I'm just saying you can solve for any one of these. It doesn't really matter what the numbers work out to be. You can solve for any one of these, right? And so instead, what I'll say we often do is we'll often write things, we'll put all the vectors on one side to not like preference one of the vectors. We'll just put them all on one side. Any It's a strange thing to do, but you'll see with the definition of linear independence that it sort of makes sense. Put all the vectors on one side. This may seem like a really silly point, but so I could also just do something like v1 plus 2v2 minus 3v plus 2 plus minus 3v2 plus 2v3 equals 0, the 0 vector, right? Yeah, I just moved these over here. Sorry, v2. That's a minus sign. Okay, and this right here is what's called a linear dependence among the three vectors. It's kind of funny. It's like I can write the 0 vector as a non-trivial combination, right? Because if I want to write, I mean, if I want to combine v1, v2, v3 and get the 0 vector, there's an easy way to do it, which is make the coefficients all 0. But this is sort of like a non-trivial way. So this is called a linear dependence. A linear dependence among, I think the right preposition is among v1, v2, v3, right? It's a non-trivial way to write trivial way to write 0 as a linear combo. As opposed to the trivial one is 0 v1 plus 0 v2 plus 0 v3 equals 0. Right, that's what I mean by the trivial linear combination. Okay, so it's a little weird, but actually I want to connect this to a couple things. Well, let me just like state the definition of linear dependence and independence first. So here's, share screen here. Yeah, if I sort of zoom in on this up here, we say a set is linearly independent if there is no non-trivial way to write the 0 vector. So I'm just saying this looks like a weird definition the first time you see it. C1, so if you have a linear combination equals 0, then all the scaling factors equal 0. But what it means to be linearly dependent is sort of the negation of that, which is there is a non-trivial linear combination of the vectors that equals 0. Okay, but what we can really say is that that really means that some vectors are a linear combination of the others. So that's kind of the point I'm trying to make here. And if I go back to the board, so definition, set v1, v2 through vn is linearly dependent if and only if some vector is a linear combination of some others. So that's the definition of linear dependence. But what I'm trying to say with this example I'm doing here is that you have to be a little bit careful because it's tempting to just say like the last vector is a linear combination of the first whatever, right? So it's not just as an example, if I took the vectors, let me just even do two-dimensional vectors, 2, 1, -1, 3, and 4, 2. Actually, sorry. I just wrote exactly backwards of what let me just put it in another order. Doesn't matter the order, but 4, 2, negative 1, 3. Yeah. Yes. Oh, that means if and only if. So when I do mathematical definitions, it's supposed to be like a logical equivalence. Like every time I say linear independent, I mean this. So IFF is if and only if, yeah. Other questions? I saw some discussion, but I'm happy to clarify. Yes. Here? No. Oh, that should be a V3. Thank you, sorry. Yeah, I was trying to solve each one for the others. Just as an example here, it's like, here's 3 vectors. It's not that the last vector is a linear combination of the first 2 here, actually, right? Do you see that? Like, how are the first 2 related? Double, this is double that one, right? So this one is actually independent of these 2, but we would still call the set linearly dependent. So this is linearly dependent. So to say some vector is a linear combination of some others, I guess I'm just trying to make the point, it's not always the last vector. Here, if this is V1, V2, V3, it's really that V2 is a linear combination of V1. That seems like a silly thing to say, but you can be a linear combination of one vector, meaning just a scalar multiple. And V3 is sort of independent. And so that's again why I'm saying we don't just write like Vn is a linear combination of V1 through Vn minus 1, right? It's not always true. So the better definition is, I mean, the saying that some vector is a linear combination of some of the others is a good intuitive definition. But a lot of times in math, you need to make a definition that's more effective, like for doing mathematics, that's more like an equation, right? And so if you can see it on the board there, like the definition of linear dependence is basically put everything on the same side. So that was the intuitive definition. The more effective definition is, this set is linearly dependent. So I'm going to start writing lin dep and lin in dep pretty quickly because of laziness. If and only if there are some constants C1 through Cn these are real numbers, not all 0. And I'm just sort of copying the definition up there, but that's important, that they're not all 0, such that S dot T dot is such that C1 V1 plus C2 V2 plus Cn Vn equals a 0 vector. Okay, so basically it's kind of what I just did up there, a non-trivial linear combination. The 0 vector is a non-trivial linear combination of V1 through Vn. Yeah. Again, the reason, because again, it's tempting to define this as saying Vn equals some, it's tempting to give an equation that like Vn equals some combination of the first n minus 1. But for example, up there, for this example that I just mentioned, the same example. What's the linear dependence? It's really that I could say 2V1 plus minus 1V2 plus 0V3 equals 0. Yeah. So again, that's also the not all 0 here. Some of them could be 0. Some of the coefficients could be 0. The set V1 and V2 is also linearly dependent here. It's a linear dependent set. Yeah.
I guess the one thing I'm sort of confused on is what the purpose of, or like the use of the set or the set, the same set without like 4, 2, or 2, 1. Both span all of R2. And
That's right.
look the same. One just has 2 of the same vector.
Yeah. So I mean, part of it is recognizing that you could throw a vector away. Like if you have a linearly dependent set, then that means you have some of this redundancy, and so you could throw something away because often we're going to want to write something and using the minimal number of vectors possible just to make things more simple. And the fact is that you would also right, if I tried to write some other vector like 100, 100, 100 as like a combination of these, I could do it lots of different ways because I can mix and match these, right? So like, it's just kind of like, it's an annoyance, basically. It's like, it actually ruins uniqueness. Like if I take this away, then 100, 100, there would be only one way to write it as a linear combination of these two. But if I leave this in, then I can do all sorts of different combinations, which all are equivalent to just the fact that this is in here. But does that answer your question? Yeah, that's like, we're gonna definitely say that. But I just want to mention that these are like the C1, C2, C3. Okay. Now, I want to connect this back to a couple things. So first off, one thing you might connect this back to are homogeneous systems. And there really is a connection to homogeneous systems here, because if you think about it, homogeneous systems is all about having a zero, zeros after the equal sign. Oh, actually, sorry, before we do that, I meant to do the definition of linear independence. So that's the definition of linear independence taken out of context just looks very strange. But it's like, how do you say in a precise way that that you have this set of vectors that none of the vectors is a linear combination of the others, right? And it seems like that could be very hairy to say, like, oh, Vn is not a linear combination of the first n minus 1, but and then the second one's not, the fifth vector is not a linear combination of 1 through 4 and 6 through 10. And it just seems like it could get to be like an annoying thing to state. But if you think about what, like in math reasoning, by the way, the other class, math 2020, we do a lot of this like logical negation. Like, how would you negate this statement? So linear independence should be the sort of the opposite of this. And the opposite of this is that if you have this equation, the only way that's satisfied is by the trivial solution. So you do get these all have to be 0. That's sort of the definition of linear independence. So, so negate the definition above for linear independence. And then this ends up being the good mathematical definition. So V1 through Vn is linearly independent literally the last time I'm writing it out fully. This set is called linearly independent if and only if. And the way to write this is that if you take a linear combination of these vectors and you get 0, then the only way that could happen, this is sort of the logical implies symbol, like this, like if that's true, the only way that's true is if all the constants are 0. Maybe I should just say this in words without been using so much logic, like only when all the CIs are 0. So basically the only way to get 0 as linear combination of the vectors is the trivial combination. Make sense? Okay. Because that actually gives us something we can sort of write down an equation and try to, if we're trying to prove stuff, especially if you're trying to prove stuff about this, it's like you, at least now if you're trying to prove some vectors linearly independent, you can write down an equation and then try to show all the phi's are 0. Right. And what I was going to say here is this also gives us a natural connection to homogeneous systems. So, for example, if we use the example from earlier, yeah, the example with these 3 vectors. If we think about this, right? If I do if I make this a homogeneous system instead, so instead of making the 3rd column the augmented column, let's augment the matrix with a bunch of zeros. This is actually, right, and this is V1, V2, V3. Then a solution to this is, or we can rewrite, maybe I should say we can rewrite as, this is equivalent to, I used X1, I almost wish I'd used X's here instead of C's. Why do I always do that? Every time I teach this, I come to the same realization at the same moment, which is that I wish I'd used X's because we were using X's earlier. This is like saying X1 V1 plus X2 V2 plus X3 V3 equals 0, right? That's equivalent. So maybe I should have, this is really our C1, C2, C3. And because this, row reduces, we know how this row reduces now. Already forgotten the constants. What are they? 3/2 and what were the 2 constants here when we row reduce this just early? -1/2 there and 3/2 there. Okay. So if we think about this, we could turn that into, so it's a slightly different thing, but we can turn this into X1 minus 1/2 X3 equals 0, right? And X2 plus 3/2 X3 equals 0. You guys did this. We did something like this. So then X3 is free. Actually, it's a good illustration of that parametric vector form thing, right? So we can write X1, X2, X3 as 1/2 X3, -3/2 X3, and X3. And we could write that as X3 times the vector 1/2, -3/2, 1. And in fact, here is this vector right here gives you your linear independence. I can plug these in for the coefficients, right? This is a homogeneous solution. This is a homogeneous solution because I can let X3 equal 1, right? And so really 1/2 V1 minus 3/2 V2 plus V3 equals 0, which I think is equivalent if I double everything, right? Is that the same equation as that? Good. So like really, it's funny, finding linear dependencies is the same thing as finding non-trivial homogeneous solutions. Yeah. Absolutely. Good. Yes. So I'm gonna say so just let me just finish this up, but yeah, I'll do that. So right, so this is same equation as before. Equation as before, I guess I multiplied through by 2. But so the idea then is non-trivial homogeneous solutions are equivalent to linear dependencies. I'll try to, let me write that down, and then yeah, then I'll do another example. We see that a linear dependence, a linear dependence in the set V1 through Vn is equivalent to a non-trivial solution to AX equals 0 where A is the vector whose columns are A is the matrix whose columns are the vectors. Where A equals this matrix. This is kind of my way of writing a matrix by its columns, right? Okay. And so, well, let's see. Does that make sense, everyone? Yeah, a lot of this class is going to be just like translating across these different perspectives, like sort of, this is about a system of equations. This is about a statement about column vectors. And we're going to have all these different equivalences. Like this should still be among. Okay, so yeah, like if I changed the third entry in the third vector there, right? So then it was no longer a linear combination. I could probably change that. Sorry, 1 second. I can probably change this 2 to anything and it won't no longer be in the same plane. Because once you choose that X and Y, there's like one specific Z that would make it in the same plane as the other two. So another example, if we did something like 4, 1, -1, 2, 3, 1, and 1 for 1,000, just to make it kind of stark. I'm not even going to go to the computer. I would just bet that this row reduces to, actually, yeah, let me do it the same kind of way I did it before. That this row reduces to like that, right? I'm just betting that like turning this number into something worse will do that. And then again, this is equivalent to x1 v1 plus x2 v2 plus x3 v3 is 0. But this tells us that x1 equals 0, x2 equals 0, x3 equals 0. Right? That's the only solution. And that's exactly what it means to be. So therefore, these 3 vectors are linearly independent. Thus, by definition, V1, V2, V3, this new V1, V2, V3 are linearly independent. Maybe I should call this like V3 prime or something, just to make it like it's a different vector than we had before. Is linearly independent. Yeah. Yes, Sydney. Yeah, there's always one thing we have to always be careful with is indefinite pronouns, right? Like it means it is this and it is this. So like if you have not a single, but like I mean, there's really infinitely many because x3 can change. But yeah, if there are non-zero solutions, non-trivial solutions to the homogeneous system, then the column vectors are linearly dependent. Right. And I could say something, I could also just say here, like, I could say a linear independence, saying that the V1 through Vn are linearly independent is equivalent to the only solution to this is the trivial solution, all zeros.
How do we know that the algorithm, how do you like interpret that the algorithm on one?
Well, so those three vectors up here were all on the same plane. And so I just figured like I've got three vectors in the same plane. So if I have a vector and I only change its z coordinate, it's going to shoot off the plane. It wasn't meant to be something. I just was trying to come up with an example quickly. That wasn't totally trivial. I'm sure if you put this into a row reduction calculator, this is what you'd get. And you could try it. I could try it. I think I closed the tab. If I hadn't closed the tab, I would just go back and change that 2 to 1,000 and do it. But yeah. So right. So also just a similar thing to this. Another conclusion. It's kind of the same. It's kind of the negated conclusion of this. If we have linear independence, then there's not a non-trivial solution, right? So V1, let's write this down here. So V1 through Vn, this set is a linearly independent set. If and only if AX equals 0 has only the trivial solution. X equals 0. I decided to just write that all the way across the board, I guess. And again, A is the matrix whose columns are V1 through Vn. Yeah. Okay, good. So this is how we can see linear dependencies. And linear independence is just convert it to a system and row reduce and see if we get non-trivial. But I kind of like that, like when you set it up by putting the 0 on one side here, that really connects immediately to homogeneous systems. Sort of shows you why this might be a good definition. Or like I said, an effective definition. We could also say something further about pivots, right? A lot of times we're going to try to reduce all these statements to just something about the pivots of the matrix that we make, either out of the equations or out of the column vectors. So how do we know if a homogeneous solution only has the trivial solution when we row reduce? What was different about the two cases here? Yeah. Every column is a pivot column, right? Yeah, here, every column has a pivot in it. Every column is a pivot column. Up here, we didn't have that. We had 2 pivot columns and a free variable. Right? Every column is either a pivot column or a free variable column. And so we could even say something further, right? So we can say we said all this, but really we just want to connect everything back to like, once we row reduce, can we get a result? Can we immediately make a conclusion? Just by looking at where the pivots are. And that's exactly right. So good. Let me write that down. All right. So also equivalently, I could have said this is like 3 equivalences. In fact, let me say it. Let me say that. So again, let A be this matrix whose columns are V1 through Vn. then we can say, I can sort of sum up all that. We can say the set V1 through Vn is linearly independent. If and only if, that's equivalent to saying AX equals 0 has only the trivial solution. I just wrote all that, but then that's if and only if the reduced echelon form of A has a pivot in every column. Reduced echelon form of A has a pivot in every column. Or you could also say no free variables. Because free variables is where we get all these extra solutions, right? Okay. So that's kind of cool. Linear independence has to do with pivot columns. Okay. Now, span, if we go back to span, wait, what time did we start? It's already 12:30. The clock, right? I've been talking for almost an hour already. Maybe we should take a break for a couple minutes. Yeah, we talked about linear independence for a while. I'm going to connect back to, I want to do something similar with span. Yeah, sorry, go ahead, question. Oh no, behind.
I was just thinking, like, if you added, so you took this example of the 1000, which will have 3 pivots indicating that it's linearly independent, right? Then you added a 4th column that was some one of the vectors there, like let's say like 2. That's still, when you row reduce, have 3 pivots, but it's now linearly dependent.
Yeah, and it would be linearly, okay, so you're saying, right, like if I added, microphone, if I add a 4th column here, what could happen? Well, you can't get another pivot, right? It's impossible. If you're in 3D, it's impossible to get another pivot. So this would have to be a free variable column. So there'd be still 3 pivots, but now a non-pivot column. So the set of vectors would be linearly dependent. Does that make sense?
So it could be a pivot column or it could be a free variable column.
Well, right. So I'm actually going to talk about that with span, but we either get a pivot column or like a 0 row. So if there's not a pivot in a column, then that's a free variable column. If there's not a pivot in a row, forgetting the augmented, then that's a 0 row. And we'll talk about that. But like, so that's actually going to be what span is all about, is whether or not there's a pivot in every row. Let's take a break for 5 minutes just to let everybody catch their breath, but that's kind of the main ideas of linear independence. I'll pause the recording. That was a lot in the recording here. Okay, so to resume, Sydney actually made a really good point just before as we're going to break, so I don't know if everyone heard it, and I wanted to write it down, which is, and I sort of meant to say this, which is that if the A right there has more columns than rows, then you can't have a pivot in every column, right? It's not possible to have a pivot in every column. So there cannot be a pivot in every column. And therefore, the columns are linearly dependent. Columns are linearly dependent. But one way to think about that is the number of rows is like the dimension that the vectors live in, right? Like in those examples, we had 3 entries in the column because there were 3D vectors. And where the vectors live the number of columns is the number of vectors that we're considering. So what this says is that if we have more vectors than the dimension, then they have to be linearly dependent. So i.e., just an equivalent statement to what we just read here is if we have more vectors than dimensions, so e.g., 4 vectors in 3D space, 10 vectors in 7D space, whatever, the vectors must be linearly dependent. Which sort of should make sense. But we kind of gave an argument why now, but it's just based on like the reduced echelon form. Okay, cool. Good, I like that. All right, now let's talk about span for a minute. I still have span at the top of that page. So a lot of times we're gonna wonder, does our set of vectors span all of the space that we're in, right? So in fact, even this same example that I've been using, it does not span, we have 3 vectors, but it does not span all of our 3, right? And now the question is why? I know I'm beating this example into the ground, but let me just do it one more time. So like, let's go back to span. If we had that set of vectors, I know them now, 4, 1, -1, 1, 4, 2, 2, 3, 1. Okay. Wait, was it 2, 3, 1? Yeah. Now let's think about augmenting this with kind of a generic column, right? We actually did this before, right? And we say when we row reduce now, we get, it's the same row reducing. And then we get some stuff here. And the point now is that this set of vectors does not span all of, this shows you the set doesn't span all of our 3 because we can choose B1, B2, B3s to make this an inconsistent system, right? I've sort of said this already, but I just want to like recapitulate everything. So again, this is V1, V2, V3. This could be some vector B. We could reinterpret this as x1, V1 plus x2, V2 plus x3, V3 equals B, right? When we talked about linear independence, we were talking a lot about homogeneous systems. When we talk about span, we're kind of talking about more general systems where especially these numbers can be anything, right? And so there are B's for which this is inconsistent. There's lots of B's. In fact, we sort of found that plane where it worked, right? For which there is no solution. Precisely because of this right here, right? This row. So the span is not all of our 3. So the span of V1, V2 is not, V2, V3 is not all of our 3. And so you can sort of see from this example though what the general case is, right? You can see that if we want, if this had row reduced to the nice 1, 0, 0, 0, 1, 0, 0, 0, 1, which I think I've mentioned once, but it's called the identity matrix. It reduces to the identity matrix. If the coefficient matrix reduces to the identity matrix, then you're good. the word all? Versus, again, let's just say versus 4, 1, -1, 2, 3, 1, 1, 4, 1,000, whatever I said, B1, B2, B3, which row reduces to 1, 0, 0. And this was V1, V2, V3 prime. So this is X1, V1. This is equivalent to and this says that there's always solutions, right? Because we can always, the system's never inconsistent. We can always solve. In fact, we can always solve uniquely. So for every B, there are X1, there are X1, X2, X3, which solve this, which work. So the span of these guys is all. Okay, and so again, it's about pivots, right? But I think I sort of already teased this. It's really about pivots in every row now. Linear dependence is about pivots in every column. Span is about pivots in every row. And so we can say it's something similar to what we set up there. So let's actually do that. I want to say something kind of similar to here, but it's not going to be quite the same. But I just want to do it like a same thing. Let A be that matrix for the column vectors of V1 through Vn. We can say the span, I guess I should say something here like the, I should write this again just so that you put it in your notes. And I guess I should say that the VIs live in R m-dimensional space. I need a different letter from n. And we do tend to call matrices m by n. Yeah.
I just have a question, like what is the prime?
The prime is just when I turn the number 2 to 1,000 in that bottom one. I'm just saying it's the same first two vectors, and I just altered the third vector. Sorry, didn't mean that to be. Yeah, I don't mean the derivative. So these all live in Rm, so m-dimensional space, right? And actually, we call matrices m by n, whereas by column, so that does work. So the span of V1 through Vn equals all of Rm if and only if Ax equals B is never inconsistent. It's always consistent, right? Because we have to be able to find, any B that we sort of augment with, because it turns into the equation, that equation up there on the left board, x1 v1 plus x2 v2 equals B, is always consistent. It's worth just writing this here that like this is really the equation x1 v1 plus xn vn equals B. That's equivalent to that, right? It's always consistent. Really means always has a solution. And we know that's the true if and only if the reduced echelon form of A has a pivot in every row. Again, I'm not talking about the augmented column. You can think about whether there's a pivot in the augmented column, but the reduced echelon form of A has pivot in every row. So this is no 0 rows when you row reduce. That's always what you're looking for when you row reduce. You're looking for 0 rows, you're looking for free variable columns. That's when stuff starts to get wonky. Does that make sense, kind of a side by side? Questions? Okay, so the last thing I kind of want to tell you today then is just about the notion of a basis, which is, well, there's a definition on the handout. Yeah. Right, so sometimes I'm using the generic V. So I do have to, we'll talk about, well, I'll say something about this in a minute, but let's just focus on like m-dimensional space right now. So what we were saying before was that like if we have too many vectors, they can't be linearly independent. Here you could argue if we have too few vectors, we can say something very similar to what we said before, that like if there are fewer columns than rows, right? Think about the case where there's fewer columns than rows. Could those column vectors span all of the space? You have fewer columns than rows. Let me just say that. Like, I kind of want to say something what I kind of just said earlier. Like, yeah, if we have fewer columns and rows, then you cannot span all of space, right? So good. So if A has fewer columns or more rows than columns, maybe I should say that's the same thing, but maybe it's more evocative to say more rows than columns, which we said is like we have fewer vectors than the dimension. Dimension is bigger than the number of vectors. Then the reduced echelon form of A must have a 0 row. Right, there cannot be a pivot in every row, because there's at most a pivot in every column. So the columns of A cannot span all of Rm. So for example, if you have two vectors in 3D, they can't span two vectors in 3D can't span 3D space, right? Okay. Cannot span all of R3. Okay, so there's this Goldilocks thing going on here where we sort of want to have like the same number of pivots as columns to get linear independence, and the same number of pivots as rows to span everything. And that's exactly what a basis is. It's a set of vectors that sort of like is both linearly independent, so you don't have any redundancy, but also spans all of space, all of whatever space you're in. So I just want to say that definition. We just end up with a lot of terminology and a lot of equivalences, at least in the first like month of this class. So, so basis, it's sort of the right vectors to span and be linear independent. So, yeah, we say the set V1 through Vn is a basis. Again, I'll just say for Rm for now, if and only if yeah, the set is linearly independent. And the span is all of Rm. Yeah.
That would just be the identity matrix.
Right, so that would be that it has to row reduce to the identity because you need a pivot in every column, every row. It actually tells you something about the relationship between n and m. Right, what is the relationship between n and m? N has to equal m, right? The only way this works, you need 3 vectors to be a basis for a 3-dimensional space. You need 2 vectors to be a basis for 2-dimensional space. So yeah, right, in fact, right, so exactly. So, wait, my brain just stopped working for a second. You said something really good and then I just forgot what it was.
Oh, just like, is it only an identity matrix?
Oh, the identity matrix thing, yeah. So, good, yeah, so this means, so basically, if we let A, thank you, if we let A, again, equal the matrix whose columns are these vectors, then the reduced echelon form of A must have a pivot in every row and every column based on the stuff we said there, right? In every row and every column. So in other words, A row reduces to, it's the only way this works to have a pivot in every row and every column is to row reduce to the identity. Right, that's what Ursula just said, and that's right. It's kind of hard to write the general identity, but it's something like, you know, the dots are weird, but that's kind of the general identity matrix. Yeah, maybe it's worth saying this is called the identity matrix. The name of this. And yeah, and this shows that n has to equal m, right? Because the only way you get this is if it goes along the diagonal, which means it has to be a square matrix. Note. This forces n equals m. So you need, right, you need the same number of vectors as the dimensions. In fact, I think I said that on here, like the way that dimension is actually defined is by the number of vectors you need for a basis. That's actually a definition of dimension. You know, think about it. At least in this realm of what's called vector spaces. That's what all these things are. Okay, good. And just as like a simple example, you know, just to make sure we're on the same page here, like IJK, that's a basis for R3. It's called the standard basis, right? And we can definitely write every vector. Well, okay, yeah. So example, the set I, J, K in R3 is a basis. But if I throw in a 4th vector, it's no longer a basis. You know, in R2, any V1 and V2 that are not scalar multiples of each other and not 0, well, 0 could be considered scalar multiple of any vector. So in R2 is a basis if and only if V1 and V2 are not scalar multiples of each other. Basically, if they point in different directions. Right, any 2 vectors that point in different directions in the plane. And you can do something similar in space. So we take any 3 vectors where they're not coplanar or not on the same line or something, then there'll be a basis for all of space. What else? What was the other thing I was going to say? There's two other things I was going to say. I lost one of them, and then now I think I lost the other one too. That was the end of 3 straight hours of teaching. Yes, good question.
What were you gonna say? What were you saying about the zero? So like it also can't be zero.
Yeah, like we certainly don't want zero vectors doesn't create much. So we don't want the zero vector in a basis. And I would say if like this is 0, then you could think of this as 0 times v2. So it would be a scalar multiple. So that kind of concludes the case. It includes the case where you're including the case that these are not the 0 vector. Yeah, what were the things I was going to say? So I remember the one thing. Well, I would just say that one thing we can talk about, and we'll talk about going forward, I'll just say it in words now, is that like you could have a plane in 3D space, and we could ask about a basis for that plane, which would be 2 vectors that span that plane and that are linearly independent. Right? So basis doesn't just apply to like Rn, n-dimensional space. It also applies to like these subspace things we've been looking at, like lines to the origin, planes to the origin. I could have some 7-dimensional subspace of 10-dimensional space. That's hard to picture, but like in the ideas you could find like 7 vectors that form a basis for that. But those vectors would live in 10 dimensions, but there would only be 7. Like in the plane example, you'd have 2 vectors that live in 3 dimensions, but we can still say they're a basis for that plane. Make sense? So that's why I'm talking about this kind of V thing more generally. It's like represents those kind of things we can have. So that'll come up more later. Oh, I guess in general, maybe another thing we're saying. Wait, let me just share screen here. One more thing we're saying is that when we go up to higher dimensions, right, we have I, J, and K for 3D, but if you want to go for like 7D, we don't have I, J, K, L, M, N, O, P, whatever. We start calling them like E1, E2, up there En, right? And that's called the standard basis. So you'll see that a lot. Oh, I remember the things, other things. Okay, thank you. The last thing I want to say is that one other way to formulate a basis, that a set of vectors is a basis, is to say that every vector is a unique linear combination of the basis vectors. There's sort of one and only one way to create. And that should make sense to create the whatever vector, like whatever B I put here. There's one and only one way to create that as a linear combination of these. That makes sense. If you're going to reduce to the identity, you're going to get a unique solution, right? So just want to say that's worth mentioning. So one other formulation. Because if you think about it, like spanning means there's at least one way to write every vector here as a linear combination. And linearly independent means there's at most one way. Because like 0, there's at most one way to write 0 as a linear combination. So you get at least and you get at most, which means you get exactly one way. So V1 through Vn is a basis, I'll go ahead and say of Rn, because we know it's the same dimension now. If and only if every B in Rn can be written as a unique linear combination. Unique linear combination of V1 through Vn. And you see it with something like I, J, and K, right? Like I can only write a vector one way as a combination of I, J, and K, right? You know you go a certain amount in the X direction, a certain amount in the Y direction, a certain amount in the Z direction. And that gives you, there's one and only one way. Cool. Okay. Good. All right. A lot of theory today, but hopefully we're seeing the grand picture so far. And now we're going to turn, on Thursday, we're going to change cat completely and start talking about linear transformations. And there is a handout, so I'll definitely be group work. So awesome. All right. Homework due tonight. I'll post homework for Friday. Yeah. I might just, there's a section in between 1.5 and 1.7 that's like applications, fixed applications. I might just give you a couple questions on that section for Friday. I'm thinking about doing that. Yeah. Just to make it a little, although maybe I've been too easy on you.
No.
All right. All right. I think, but then you kind of have to like read that read a couple examples in that section and do it. As a mathematician, I don't want to do applications. We'll do some cool applications later in the semester. This is just some basic applications. Like the chemistry stuff is one of the applications they do in that section. All right, we're done. Thank you. I have office hours later. Oh crap, I didn't stop the share. Yep. So,
Are you gonna upload the problem set today?
yes, for Friday. Yeah, some point. Okay, good. I don't think I finished. I don't think I went back to the board when I defined a basis. So sorry, let me just do that real fast. It's a pleasure. Have a joy. Thank you. You too.
Thank you.
This is a basis stuff. Sorry, I don't think I went back to the board. So I wrote the stuff here about basis. Sorry, I think I was on the screen share. And then I wrote this stuff here about it. And so I was talking. This is what I wrote. Sorry about that.